Okay, I'm going to talk about 2.3 today, product and quotient rules and higher order derivatives. We're basically, the big part of this section is just continuing on in our derivative taking skills. Once again, we don't want to use definition or derivative for everything. So as we talked about in the last section, we have power rule and some other rules that we discussed. And then today we are going to talk about some other situations. The first of which is going to be product rule, okay? One of the most common errors is that people will believe, that if I want to take the derivative of, let's say, this, and just, I'm going to put this aside, I'm not even sure if I want you to write this down, even though I tell you to write down everything for your notes. If I'm going to take the derivative of this, y prime, or dy over dx, and I'm going to talk about that notation here in a moment, could I just take the derivative of this and multiply by the derivative of this? So is this equal to just 4 times 8? So the derivative of this is 4, the derivative of this is 8. So could I just take the derivative of those things and give us 32? And the answer is definitely no, okay, which I'll show you in a second. That does work with adding and subtracting. I can, if I have a bunch of things added and subtracted, I can break them into the various parts and then add or subtract their individual parts. It doesn't work with multiplication and division. So this one's easy to see because we can go ahead and simplify this and put this into a form that we can take the derivative quite easily. So this is going to be 32x squared plus 4x minus 1. Did I do that correctly? I hope so. Looks good. Let me know if I make any errors here. A lot of room for error in today's, a lot of arithmetic and things like that. So if I take the derivative here, I get 64x plus 4, and obviously the 32 is not the derivative. Those are two very, very different functions. So we cannot just simply take the derivative and of the one part times the derivative of the other part. Same is true for multiple or division. So product rule, the rule is if I want to take the derivative of the product, you take the derivative of the first factor, copy down the other, and then plus, and then you switch it. Okay, so that is product rule. Take the derivative of one of your factors, okay, copy down the other. So let's see if this works. Copy down the other, and then switch it. Take the derivative, and reverse the process. I got lost there along the way. Hopefully you understand what I'm saying. So let's go ahead and try this and see if it works. So we're going to take the derivative of this one first. So that's 4. Copy down the other factor. Plus, now we take the derivative of this factor, 8. Copy this one down. Let's simplify and see if this gives us what we're looking for. So that gives us 32x minus 4 plus 32x plus 8. Combine a little like terms there. Y prime is equal to 64x plus 4. And there you go. We're getting the same thing. So that is good news. So that is how we do products. Okay? And now we can do all sorts of functions. So for instance, if I gave you the function 4x squared sine x, now this one we could have done without product rule, this one we can't. So we have two factors here. How do I take the derivative? Take the derivative of the first factor, that's 8x, copy down the other, plus, now switch it. Derivative of sine x is cosine x, and copy down the 4x squared. A lot of times we write that 4x squared in front, but it doesn't really matter. And there you go. That's product rule. Okay. Let's talk about quotient rule. Okay. Now we're going to talk about quotient rule. So if I take the derivative of a quotient, okay, the way we do this is we square the bottom. Okay, so whatever the bottom is, we leave it alone. We just square it. Take the derivative of the top first, copy down the bottom, minus, and then you switch it. So the top sort of looks like product rule, except to have the minus instead of a plus. The only thing that's important is, because we have a minus, and minus subtraction, I should say, is in commutative, it's important that, that we follow the correct order. So you take the derivative of the top first, copy on the bottom, minus, and then the opposite. Product rule, doesn't matter which one you take the derivative first, because it's plus or addition, which is commutative. Okay, so what is that going to look like? So let's say I have the function 5x plus 1, 3x squared minus 5. If I take the derivative of that, dy over dx, by the way, just different notation. And I'm going to talk about where this notation comes from. It means exactly the same thing as y prime, but this is a notation you're going to start seeing, and I want you to be comfortable with it. So anyways, square the bottom. Take the derivative of the top first, so that'll be 5, copy down the bottom, minus, take the derivative of the bottom, that will be 6x, copy down the top, and there you go. So that is quotient rule. What else do I want to say about that? Oh, if we're just sort of churning out derivatives here, go ahead and leave it like that. I do know I was looking at Delta Math. Some of them, they do want those simplified. So if you're specifically asked to simplify, simplify, but if not, if there's not a compelling reason to simplify, then don't worry about it. You know, I will tell you that if we had to work with these derivatives, it's often going to be easier if we do some simplification. All right, now the one thing I want to say about quotient rule is once people learn quotient rule, they kind of can make things more difficult for themselves. Because let me just give you an example of a problem that you could use quotient rule, but it's much easier not to. So for instance, let's say I gave you the function y equals, let's go with 4 over 3x squared. I could use quotient rule for that. However, I can rewrite this thing so I can use simple power rule. Okay, so 4 over 3, I call that 4/3, and then x squared in the denominator, I'll call x to the negative second. I don't need quotient rule to do this. In fact, quotient rule is going to make this uglier. Bring this down, multiply it in front, that'll give us negative 8/3, x to the negative third. And if we had to simplify it, it's going to be a lot easier than if I did it if I did it as quotient rule. So a lot of these that you're going to see along the way, if you can find a way to do it without quotient rule, it's not a bad idea. Okay. The next thing we're going to do is we're going to do all 6 of the trig derivatives. So we already know sine and cosine. The derivative of sine is cosine. The derivative of cosine is negative sine. But we're going to do the other 4 as well. Okay. Okay, so here are the 6 trig derivatives. The good news is this semester, unless I say otherwise, but I think I'm pretty much settled on the idea this first semester you're going to be able to use notes. Eventually these have to be memorized because my anticipation is for the AP test, you're not going to have notes, and these are things that typically we have to know without notes. So they can seem quite tricky, but there is actually a pattern here. So I want to point out to you that sine x, tangent x, and secant x, I don't normally sort of couple those together. I usually think of sine, cosine, tangent, and then the reciprocals. But the reason why I do this is because there is a pattern here. Let me point out that these are the co-functions over here. So sine, cosine, tangent, cotangent, secant, cosecant. If I remember these 3, so the derivative of sine is cosine, the derivative of tangent is secant squared x, and I just have to memorize these. The derivative of secant x is secant x tangent x. Then I can, as long as I know this pattern, I'm going to get these as well. So if I look at cosine, okay, I think of what its other function is, its co-function is, which is sine. Okay, secant squared x, well, what is its co-function? Cosecant squared x, and then the same thing here, secant x, cosecant x, tangent x, cotangent x. So that's a pattern that makes it really helpful, where it's basically I just have to memorize that 3. And then also I want to point out that the derivative of all your co-functions are negative, where the derivative of your functions that are not co-functions, don't have the co in front of it, are positive. So those are our 6 trig derivatives. You know, for the time being, you know, you're going to be able to use your notes for these, but memorizing these is a good idea, because I don't want it to be like the second semester when we start memorizing, you're gonna have like a mountain of things to memorize. Because as soon as that second semester starts, we're gonna have to start pulling away from the notes, okay? So you have product rule, you have quotient rule, and you have these 6 derivatives. Hopefully you have those all organized on your notes. What I'm gonna do now is I'm gonna do a bunch of these derivatives here where I'm just gonna be mixing everything in together. All of this at once, and we'll go from there. Okay, I'm going to do these 7 examples. I'm going to do them relatively quick. The thing about these rules, these derivatives, it really is one of those things that at first it's going to be challenging. As you practice these things, you're going to find it gets a lot easier. This is a skill we'll be using all year, so I'll have a lot of time to get better at it. Okay, so if it comes a little slower to you, don't worry too much. It's just something you just have to keep practicing. And we're going to be doing a lot of these. If you notice, you will notice when you see the textbook problems. I am assigning a lot of these because this is really just about practice. Okay, so let's just go ahead and go through these. So the derivative of this is going to be 6x. The derivative of cosecant x will be negative cosecant x cotangent x, but we're subtracting that so we can make that plus. You could leave it minus a negative if you want, but you know, in my mind that's cleaner. So the derivative of 3x squared is 6x minus the derivative of cosecant x is negative cosecant x cotangent x, so that gives us the plus. Okay. Here we have to use product rule. So product rule once again, take the derivative of the first thing, that'll be 3x squared, copy down the cotangent, x, plus, and now we're going to switch it, copy down the copy down the x to the third, and now let's take the derivative of cotangent, that'll be negative cosecant squared x. Now, of course, I could have made that a minus instead, but it really doesn't matter. Unless you're specifically asked to simplify, you know, leave it in a form like that is not a problem at all. Okay, this one here, we're going to use quotient rule. Hopefully I have enough room. We'll just go for it. So it's g prime of t. We're going to square the bottom. The bottom stays intact. We're just squaring it. Take the derivative of the top. So that's going to end up giving me 4t. Copy down the bottom. Hopefully that's not too ugly for you at home. So 4t, copy down the bottom, plus, minus. Quotient rule, we do minus. And minus, take the derivative of the bottom now, which is 3, copy down the top. So it'll be 2t squared minus 1. And that is quotient rule. We're just going to leave them like they are for right now. We have another quotient rule here. So square the bottom. I'll just call that t to the 6. Take the derivative of the top. That'll be negative sine of t. Okay, copy down the t to the third. Just to make it a little cleaner, I'll put that out in front. Okay, so take the derivative of the top. That's negative sine t. Copy down the t to the third. Minus, now let's switch it. Take the derivative of t to the third. That'll be 3t squared. Copy down the cosine t. And there you go. Once again, if I make an error here, you know, obviously I'm doing a lot of computations. If I make an error at some point, please bring it to my attention in class and we'll address it. Okay, now let's take the derivative of this. So this we got to use product rule on. So y prime is equal to the derivative of x is just 1. Copy down the sine x. We don't need the 1 there because multiplying by 1 doesn't do anything. Plus, now copy down the x. The derivative of sine x is cosine x. And then the derivative of cosine x is negative sine x. Now I could obviously simplify this because these things will zero out and that leaves me with x cosine x. But, you know, it just depends if you're asked to simplify or not. Okay, this one here, y prime is equal to square the bottom, the denominator. Take the derivative of the top. The derivative of 2e to the x will be 2e to the x. Copy down the bottom, x squared plus 1. Minus, now let's switch it. Derivative of x squared plus 1 will be 2x. Copy down the e to the x. Okay. This one, I'm going to give myself some more room here. So hopefully you got these. If not, go ahead and pause and make sure you get those down. So number 7 is a good example of a problem. I could use quotient rule. However, I don't need to use quotient rule. I can rewrite this thing. So that's what I'm going to do now. Okay, number 7. I'm going to rewrite this one. So what I'm going to do is this. First of all, we can distribute that 2 up top. So this is going to be 2x to the third minus 2x squared. That's all over 5x. Now, one of the patterns you're going to see is, and this is something we're going to see quite a lot of in this course, and it's something you want to get used to. If I have a polynomial, multiple things in the numerator, over a monomial, okay, I can always split that into the various parts. So I can call this a over d plus or minus b over d plus or minus c over d, and I can split that up. So here, I can go y is equal to 2x to the third over 5x minus 2x squared over 5x. And now I can just put this in a form I can use power rule on, which is going to make this a lot easier. Also, if you're thinking, oh, well, quotient rule is easier for me, just keep in mind, especially if I had to work with this thing, the derivative I'm going to get here is going to be much, much nicer than any derivative I'm going to get from quotient rule. So it is a good practice to get into when we have these problems we can rewrite and not use quotient rule. It's a good thing to do. So 2 over 5 is 2/5. X to the third over x is x squared. Minus 2 over 5, that's 2/5 again. Okay? And then we have x squared over x is x. Now, let's take the derivative. So that'll give us 4/5 x. Really easy here. And that is a pretty nice derivative. Okay? So like I said, if that was a little overwhelming, I went through those kind of quickly. Just know that it's not something you have to get all at once. It really is going to take practice on your part to get good at these. All right? Okay, the last thing we're going to talk about today is higher order derivatives. For the most part, the idea itself is pretty easy. I'm also going to introduce you to some different notation here that looks quite strange, but it's something you'll get used to pretty quickly. There's a lot of applications for higher order derivatives. So higher order derivatives, let's just say I have f of x, and let's just go with 3x to the fourth plus 3x squared minus 8x plus 2. And the first derivative, call it f prime of x, is equal to, 4 comes down, that's 12x to the third plus 6x minus 8. And then a higher order derivative is we can take what is called the double derivative, which is just a derivative of the derivative. And in the coming weeks and months, we'll talk about why we need multiple derivatives in certain cases. Right now, we're just going to practice doing that. So we just take the derivative again. So that gives us 36x squared plus 6. And then we could even go to the third derivative. I will point out when it comes to polynomials, at some point, they're always going to go to 0. So take the derivative, that's 72x. And then if I take one more derivative, the fourth derivative, and I can just keep going, that's 72. If I take the fifth derivative, and notice, once we get past 3, we typically just denote it with a little number in parentheses. This is 0. With polynomials, it's sooner or later you're always going to get to 0. There are functions, for instance, y equals sine x, where you can keep taking derivatives over and over again, and it's never going to decompose to 0. Okay, and that'd be negative cosine x. So that's all it means to do higher order derivatives. You're just taking the derivative of the derivative. Okay. I want to point out that our friend e to the x, this one, you take derivatives all day. Take the 100th derivative, it's just e to the x. So derivative of e to the x is e to the x. Keep doing that, you get e to the x. Okay. So let's talk about some notation, and that will do it for today. Okay, some notation. We are all familiar with the y prime, that's the first derivative, or f prime of x. Okay, another notation you're going to see a lot of, like for y prime, would be dy over dx, and I want to talk about what that means. So I think the best way to do is look at a graph here. This really kind of has the definition of derivative built into it. So if we think about what we do here, let's say I want the derivative at x, right? what we do is we start with the slope of a secant line, okay, rise over run. The whole thing of dy over dx is dy over dx. This means something very specific to us in calculus. So we know that when we do definition derivative, we take those 2 points, the slope of the secant line, and then we limit them together. This notation has that idea based into it. Dy means an infinitesimally small change in y. Infinitesimal is sort of the reciprocal of infinity. So infinitesimal is something that's approaching 0 versus infinity, which is something that grows without bound. So infinitesimal is something getting closer and closer to 0. You could think of it as being the thing that's the closest number to 0 if such a number existed. There is no such number. You choose a number that you think is the closest number to 0, and I can find a number that's closer, and we can play that game all day. So this notation means an infinitesimally small change in y over an infinitesimally small change in x, and basically has the whole idea of rise over run, but we're limiting those points together built into it. So this notation just means derivative, okay? When we get to the double derivative, it looks a little funky, so let me talk about the double derivative. So let's say we're taking the derivative of our derivative. Now, when we take the derivative, the independent variable is still x, but the outputs are dy over dx. We're going to do this same thing again, okay? Except now, so this will be dx, the derivative of, or the change in this will be d of dy over dx, okay? So our double derivative is actually the infinitesimally small change in dy over dx over and then dx. Now, this gets a little silly, but take note, the notation, what they end up doing is they call this d squared y. So just think of like 2 d's, we get d squared y. And then dx divided by dx, that's dx squared. So this notation means a double derivative. And then this just keeps going. The third derivative might be denoted, nope, not with a 2. The third derivative would be the same thing, but with a 3 instead. And once again, this is just something that you need to know what it looks like. You'll see me from time to time write things in terms of dy over dx. It really doesn't matter in most cases. We'll talk about when it does matter, but whether you call it dy over dx or y prime really is insignificant, generally speaking. Okay, so that is section 2.3.